So hello everyone. So in this presentation, I will talk about some of my PhD work. So with David Makowski and Philippe Sier. So we are trying to develop a methodological framework to predict maize yield and prices using remote sensing data. So I will first explain why we are doing this with some context element. And then I will explain how. So I will talk about the method and the data. Then I will show some results, then the conclusion and some perspectives. So first, some context. If we look at what has already been done, we see that there is quite a lot of paper, a lot of people who have studied the relation between the maize prices and supplies, the production. And they all reach out to the conclusion that yes, there is a relation between maize prices and the production. So that's not very surprising. But what is interesting is that some papers also found that the US production has a significant impact on the on the global prices. So that means that theoretically, if you only know the US production, you might be able to predict the global prices variation. And actually, there is publicly available data on the US production. So you might wonder, why are we doing this work? It's basically because the data on the US production are only available at the very end of the season. So if you want to make some prediction, you will have to wait until the very end of the season, which is quite limiting. So this is where we step in with our remote sensing data, because we are able to monitor, to evaluate the vegetation and the crop condition. So how do we monitor the crop? Well, it's mainly based on the spectral signature. So if you look at the plot at the bottom, you will see that, for example, an LC plant will have a stronger reflectance in the near infrared than a stressed plant, while a stressed plant will have a stronger reflectance in the red than an LC plant. So mainly based on these characteristics, you can then compute some vegetation indices, such as the normalized difference vegetation indices, the soil adjusted vegetation indices, and many more. You can even estimate some biophysical parameters, such as the leaf area index, the fraction of absorbed photosynthetically active radiation, the fraction of vegetation cover, and many more. And which is even more interesting with the remote sensing data is that you can have data about almost the whole planet for free. And for some places, you can even find daily data. So I just put two examples to illustrate how you can monitor the crop. So on the left, you will see a map of the leaf area index of July 2012. July 2012 and the summer 2012 was very bad. The weather was very bad, and the yield was very low that year. And on the contrary, on the right, you will see a leaf area index of July, but 2016. And in 2016 was quite a good year. The yield was quite high. And now, if you look at both images, you see that in 2016, the value are much higher. You will see a lot more green areas. And that's because the leaf area index gives you information about the crop condition. So which brings me to our ultimate goal. I have already talked about it a little, but we want to predict the impact of the maize production variation on the prices using remote sensing data available during the season. So what is important here is during the season, because it will pave the way to real-time price prediction. It will make possible to avoid the use of third-party data report on the crop condition, on the crop production, on the demand, and maybe ultimately you might even be able to anticipate food crisis, because if you are able to anticipate shock production, you might be able to anticipate food crisis. So to do that, we have several types of data. So first, we have some remote sensing data. So we have the leaf area index. So from 1988 to 2018. So at a spatial resolution of 0.05 degrees. We have data every 8 days. We have also a maize mask, so from the USDA, so the US Department of Agriculture. It has a spatial resolution of 30 meters. And obviously, we have data on the maize prices, and we have data on the US yield. So we have data on US yield because it will be our study area. So more precisely, it will be a sub-region of the US. We call it the Corn Belt. So if you look at the map on the left, you will see that part where there is a lot of production, of maize production. We see a lot of dark green. This is the Corn Belt. And the Corn Belt produces approximately half of the US production, while the US produces itself approximately a third of the world production, which explains why the US production has a significant impact on the global prices. So now, I've said that we want to predict the maize price variation. So we first need to compute the annual price variation. So we call it delta P of MT. So to compute it, we simply take the price at month M for the year T minus the price at month M, but at T year minus 1. Then we divide by the price at month M, but at the previous year. We did the same thing for the yield, except that for the yield there is only one data per year, so you don't have months. So you just take the yield at year T minus the yield at T minus 1 divided by the yield at the yield T minus 1. So this is the first step. Then in the second step, we define some binary variable. So we call it delta PB of MT. It takes the value 1 when there is a price increase. So there is a price increase when delta P of MT is greater than 1. And it takes the value 0 when there is a price decrease. And there is a price decrease when delta P of MT is lower than 0. Then we do the same thing for the yield. And this is the two variables that we want to predict. We want to predict the price variation and the yield variation. And we want to predict that using our leaf area index. So to illustrate that, let's say that this matrix X is the leaf area index. So we have in row the time. So we have 38 years, so we have 38 rows. And we have in column the number of pixels, the spatial location. And we have a lot of pixels. So we have more than 100,000 pixels. And with this pixel, we want to predict one price variation or one yield variation. So this is a bit inconvenient. So we try to first reduce that number of columns, that number of pixels. There is many ways to do that. Maybe the most basic or the simpler way is simply to make a monthly mean, so over the pixel. So you have your leaf area index at month M, and you simply take the mean. So instead of having thousands and thousands of pixels of column, you will have one value per year, per month. And then with this value, you can try to predict the price variation and the yield variation. So this is a way to do it, but it may be too basic. So we also try to a more advanced technique, more advanced method, which is called the empirical orthogonal function. So this is a method that will decompose your data using a singular value decomposition, and it will decompose your data in spatial mode or spatial pattern. We call it UFK, and in its expansion coefficient or principal components. There is many names, and we call it A of K. So in the output, you will have two types of data. So a spatial mode, so on the left, so it's a map, you have one value per pixel, and you will have a time series, so principal component or expansion coefficient. And this is what we use in our model to predict the price. So this is the A of K. So in our model, we currently use a generalized linear model. So if we take the price prediction model, so we want to predict the probabilities of increase. So remember, decrease is 1. So we want to predict the probabilities of 1 using our expression coefficient A of KT. Then this is the same principle for the yield. We want to predict the probabilities of increase. So increase is 1. We want to predict the probabilities of 1 using our expression coefficient AK of T. Then we also did variable selection using lasso. So lasso is it will simply shrink some variable coefficient to 0. It will select some variable. Okay, and we also did leave one out cross validation. So it's a method of cross validation. In our case, for example, we will set apart 1 year. It will be the test set. Then with all the remaining year, we'll train the model, and we will then try to predict the test year. And we repeat this step t times. So t is year. So we repeat this step 38 times. And then we compute the metric score using the prediction that we have stored. So we use the area under the curve matrix. So this is a performance matrix that will evaluate the performance of the model. So basically, if you have a score, for example, the 0.5, it means that your model is extremely bad. It's similar to a random guess. But while if you have a score of 1, it means that your model is excellent. You make a perfect prediction. So the closer to 1, the better. So now if we look at some of our results, let's start with the maize price variation using the if area index means. So the table is a little bit complex, so I will explain it. If you look at the row, you will see there is a list of months, March, April, May. This is the price that we want to predict. If you look at the column, you will see there is LAI, then the months. For example, LAI May. This is the leaf area index mean of May. Now, how do we read the table? So, for example, we see that we cannot predict the price variation of June using the leaf area index of May, because the score is very low, it's very poor, it's 0.57, that's not good. Remember that 0.5 is similar to random guess, so that's very not good. But what you want to look at, it's first the color. When it's red, it's not good, but when it's green, it means that the score are higher. And then you also want to look at if the score is in bold or not, because when it's in bold, it means that the confidence interval is significantly different to 0.5 to a random guess. So what we see in this table is that the overall score is very, very bad. It's very poor. We cannot make accurate prediction of the price variation using only the if area index mean. The score average not good. Now, if we compare to the result of our model, so the table is similar. We have still the monthly prices in row. In column, we have the input predictor. So, for example, we have the UF April. So this is the output of the empirical orthogonal function computed from the April LAI. And we see that the scores are much better, much higher. For example, we can perfectly not perfectly, but we can predict high accuracy the price variation in October with the OF of April. They have a very high score, and the OF April works very good for all the months from May to December. And we also see that we have quite a good score in the early season. So even in March, we have quite a good score. So keep that in mind. We'll talk about it later. But first, we will look at the yield result. So if you want to predict the yield variation using the leaf area index mean, the table is a little bit different. This time, the month does not represent the price that you want to predict, but they are the months of the leaf area index mean. So, for example, if you look at February, you see that the score is 0.53. That means that with the mean of the leaf area index, you cannot predict the yield variation because the score is extremely slow. Extremely low. And overall, all the score are extremely low. We cannot make any good prediction with the product means. But now, if we compare with the model, our model, we see that we have much higher score. We have a good score in February, in May, in June, in October. And what is a bit surprising and odd is that we have a very good score for February. It's very early in the season. Usually in the US, it depends on the state, but usually the season starts in April and it ends in November. So that means that in February there is no corn, so you don't monitor the corn. But we have a theory to explain that. We think that the data in the early season highlight the late winter or the early spring sowing condition. So we think that for two reasons. First, because we've seen a recent paper, which shows that the weather in the late winter, early spring have an impact on the soil quality, which will have an impact on the corn yield. And also because we know that the weather in early spring have an impact of the start of the season. And we know that the start of the season will have an impact of the yield. Typically, you have an optimal window where you should sow your maize. And if you don't sow your maize in this optimal window, you will have a lower yield. So yeah, just to conclude, so we've seen that we can develop some model using remote sensing data for an early forecasting of annual increase and decrease of maize yield and maize prices. We also seen that our model using the EOF give better result than using only the leaf area index, and that the early data, the data in the early season, April and March, probably highlight the sowing condition. So next, for what we want to do next, we want to try to experiment different dimension reduction method. So far we have used EOF, which is a linear transformation, but there is some method, some way that can take into account non-linear relation, such as the variational autoencoder, which is a type of neural networks. Then finally, we want to try our approach, our method on other type of crops and region. Why not try the wheat durum in Canada? So Canada is one of the main producers in the world, and the production is relatively constrained in a small area. Soybean as well. USA is once again one of the larger producers, and it is grown in approximately the same area as maize. I've seen some paper which use the word now corn soybean belt instead of corn belt, and the rice as well in Asia. Thank you.
Do you plan to test the sensitivity of your method to the chosen LAI product?
Not really. We don't think about that. But it could be a good point. But yeah, could try. But we also try with different products. In this presentation, I have only showed the if area index, but we also try with the GPP and the FAPAR.
I think one issue you have, Florian, is the length of the time series of satellite products available. So you need a relatively long time series to test your method. So I think that this is why you
that's why
you choose GLASS, no?
Yes, that's why you choose GLASS, because we have 40 years of data. If we use MODIS, we will only have 20 years of data, so we will have a shorter time series, and we prefer to have a long time series to develop model and make prediction. So,
okay. And so you know the droughts are increasing. So for example, if you take imagine we would take some production in France, and so because of the drought in the summer, I mean, the production was probably catastrophic, and then you wouldn't have a relationship with some information in February.
yes, that's a good point.
So are you only working on well-watered crops and so?
No, we don't make any distinction between irrigated area and non-irrigated area. If that was the question. Or...
Yeah. Okay. Thanks.
Any other question? Personally, I'm quite surprised that we are able to not to predict prices, because you don't predict prices quantitatively, but you have to classify whether the price will increase or decrease. So I'm quite surprised that you are able to classify increase or decrease of prices in fall from remote sensing data collected in spring. That's a very interesting result, not fully expected to me at least. So yeah, so if it's confirmed, I think it's a very interesting result. I think we need to confirm it, but still it's quite impressive. Yes, Lauren.
Yeah, sorry, I have a question about the presentation. How did you find the borders of the crops? Were they already in a database?
You mean the corn mask, you mean?
Sorry.
The border. The border, you mean the corn mask? You mean a mask to delimit the crops?
Yes.
We use the data from the USDA. They produce a corn mask.
Okay.
It's freely available. But
Okay, thank you.
that's also an issue for us because they don't have corn masks for every year since the 1981. So we have a static corn mask. That's a limitation.
Mm-hmm. Okay, I understand. Thank you.
I think you also, you didn't show that, but you also tested your models using data collected not at the Corn Belt scale, but at the national scale. Huh?
Yes.
Can you give some details about this?
Yes. Overall, the results are not so much different. I remember that we see the same pattern. So we have good prediction in the early season, so in March and April. The same pattern. So if we have the same or almost the same result, it's probably better to just choose the Corn Belt because we have less data, so it's less computing intensive. So it's faster. So maybe it's better to just choose the Corn Belt data. Because like I said, the Corn Belt produce approximately half of the US production. So that's quite huge. So yes.